I'm Mark Callahan. I work on a variety of RocksDB projects, mostly on efficiency and performance and quality of service at Facebook. So for a long time, I worked on MySQL, and I still do, but I was strictly MySQL and InnoDB for a very long time. And probably over the last 6 years, on the side, I've spent time doing evaluations of other storage engines. So I've been dealing with TokuDB, not in production, but in evaluation for about 6 years, and WiredTiger, maybe 3 years. When MongoDB first came out, just maybe out of boredom, I was curious about it, started to follow what they were doing, and then was very excited when the engine API came out for pluggable engines, and RocksDB team and the WiredTiger team quickly implemented a MongoDB engine. And the nice thing is the engine API for MongoDB is much easier to implement than the MySQL engine API. A lot of things that are pushed, a lot of responsibilities that MySQL pushes down to the engine are done above the engine. So it took about 1 year to implement and get MongoRocks running in production at Facebook. It is no longer running in production at Facebook because we're not running Mongo, but I still like the product. And so I stay involved. I continue to do performance evaluations for MongoDB, not as actively as I used to, but for this conference, I spent a few months running tests. One thing I want to point out is we continue to make RocksDB a lot better. There's a lot of engineering time continuing to be invested in RocksDB, and much of this work directly benefits the MongoRocks engine. Some of the things that we have in progress, we are adding support for direct I/O. If you're a database performance person, it's much easier to reason about and monitor I/O performance with direct I/O than it is with buffered I/O. Smarter compaction, we recently had a change that for some of our workloads cut the write amplification rate in half. So we're writing half as much to storage as we used to. This change is not yet, well, it wasn't in Percona server 342 that I've been using. We are working on support we'd like to run databases that are 100 to 200 times the size of memory. And the working set is not going to fit in memory in that case. And so we have to adapt RocksDB to be more effective in limited memory environments. We've done a lot of work to reduce response time variance. We still have more jitter compared to InnoDB. The comparison with WiredTiger is a bit easier. InnoDB is much more mature. So we continue to become more competitive if you care about quality of service, and there's a lot more work in progress. My pitch for MongoRocks, and I say this, I'm a huge fan of WiredTiger. I speak to Keith Bostick and Michael Cahill, the founders. I speak to them several times a year. When I'm doing performance work, I frequently give them direct feedback first to see if I'm doing something dumb. But, and WiredTiger has an LSM, but it's not officially ready for production. So if you want a right optimized engine, MongoRocks is a choice. Best space efficiency. And so MongoRocks will use the least amount of space of any of the production quality storage engines. Because it's using leveled compaction, which wastes the least amount of space. Better write efficiency. So it's not if you measure the write rate to storage per transaction, MongoRocks or RocksDB is hard to beat with what we're using with leveled compaction. It's definitely much better than a B tree. Good or good enough read efficiency. And here's maybe where I'm using weasel words or hedging. The question is, if you want the to favor space and write efficiency. There's potentially no free lunch, and in some cases, you will pay with more CPU and I/O on the read side. For some of the workloads we are running in production on MyRocks, we're actually not seeing that overhead, but there's definitely benchmark results I can show where B trees are more efficient for reads than an LSM. And then the last point, it's effective with SSD or disk. So we've been marketing RocksDB a lot as the database engine for fast storage, but it's also really good for disk. And the big selling point if you're using disk is that we are more efficient on writes, and so we save more I/O capacity for reads compared to a B tree. These claims I make about efficiency. Why is, if we're talking about RocksDB, which MongoRocks uses, compared to a B tree, and WiredTiger is a copy on write B tree, why is MongoRocks more space efficient and more write efficient? And then how do you think about read efficiency? So for space efficiency, the number one win is that with a B tree, subject to random operations, the leaf nodes will be half full over time. And so half full means you're using twice as much space on disk or SSD, and the leaf node pages that are in the buffer pool are also wasting potentially half of the memory. So if you tried to think of fragmentation in terms of an LSM where at most we're wasting about 10% of the space, both on disk and in memory. If you use compressed NODB, which we happily have been using for years, there's a fixed page size on disk. So if you have a 16 kilobyte in-memory page and it compresses to 5 kilobytes and you're using a 2x compression with NODB, the 5 kilobytes has to still take 8 kilobytes on disk. WiredTiger, the copy and write B tree, it's a little bit hard to think about they don't suffer as much from the fixed page size, but I'm not going to go into depth on that. Per row metadata. So a B tree, with RocksDB, the per row metadata is 6 or 7 bytes. For the majority of the entries in the LSM tree, we compress it to 0 bytes. Only for recently written data is that metadata going to take up space. Key prefix encoding, with RocksDB, actually, and with WiredTiger, both are doing key prefix encoding. If you have common prefixes between keys, we can compress that away, and that's done both for the on-disk format and the in-memory format. Write efficiency. So a big difference is if you're using less space, which we are with RocksDB, you have less data to write. Both WiredTiger and NODB will be using more space on disk. There's just more pages to write when the database becomes dirty. A key point is that for many of the workloads I care about, we have fast storage. So we have MLC NAND flash devices. Let's say they can do 50,000 IOPS or more. If you have fast storage, we want to take advantage of it, which means we want to make the database as large as possible relative to memory. The working set might not fit in cache. With a B tree, the worst case is if you're writing back dirty pages that only have one modified row. So if you have a 16 kilobyte page and a 256 byte row, the write amplification from there is a factor of 64. The size of the page over the size of the row. The last point, the double write buffer, it's not an issue for WiredTiger. It is an issue for NODB and for mmap, not for mmap. So I can skip that. Read efficiency. Read efficiency, if you look at what an LSM tree has to do, there's potentially more data structures you have to search on range queries and point queries. And so you can spend more on CPU and more on I/O, but it's not always the case. We fit more data in cache because of more efficient encoding. Better cache hit rate, we're doing less I/O. Now the Bloom filter means we can skip many of the reads to some of the file structures. Another example is we are spending less on writes. We are more write efficient, so we have more I/O capacity for reads. And this is an issue with disk arrays and even with what I would call slow SSD, so TLC, lower endurance SSD. Let's say you have a device that can do 10,000 IOPS. This property is very valuable. And the last point is non-unique secondary index maintenance with RocksDB is read-free. We don't have to do a read before the write. We just blindly do a put into the mem table. The B trees have to read the leaf node pages, modify them, make them dirty, eventually write them back. So update heavy workloads, if all of the secondary indexes don't fit in memory, update heavy workloads can be much faster on RocksDB. Now, I am always cautious about talking about performance. One of the things I do is unofficially, I market things. I used to market bugs that I wanted Oracle to fix. There's not as many bugs that I have to market anymore, and I just moved on. Now I market RocksDB, MyRocks, and MongoRocks. So I do what I call bench marketing. A lot of people do it. And bench marketing, or I'm careful about doing it. Bench marketing is using impressive results and saying X is faster than Y means X is better than Y. And so I will point out when I'm doing it. If I have time, when I speak about performance, I try to evaluate throughput, efficiency, and quality of service. I don't want to just put one bar on the screen and say we're faster, we're better. I try to explain why. Here's an example where average throughput for MyRocks is pretty good. The problem is there's a lot of variance in that graph, too much variance. And that's from several months ago. We've improved. We still have room to improve. But this is an example where if I just gave you the bar for average throughput, it might be impressive. That's not impressive. For MySQL, I run the insert benchmark, link bench, and sysbench. For MongoDB, we have link bench, but MongoDB doesn't support transactions, so I don't run it that much. I do run the insert benchmark. The insert benchmark, I run it in 3 phases, and this is what I will be providing results for. The 3 phases, step 1, insert only, usually with concurrency. A table with 3 secondary indexes. Inserts are in primary key order. The secondary index changes or not. So there's a lot of random I/O potentially for the secondary indexes. When the load finishes, then I run, let's say, n insert clients and n query clients. And n is frequently 16. Each insert client is rate limited initially to 1,000 per second. So with 16, my insert clients totally should be doing 16,000 per second. And then I try to let the query clients run as fast as possible to see what query throughput I can get. And then I repeat that test where I reduce the rate limit to 100 per second per insert client to leave more room for reads. I've been running this for a decade. Every engine that I've spent time running this has had very simple workload, but every engine has had significant problems from this. This is can be very intensive on anything with a block cache or a buffer pool. You have a lot of reads coming into the buffer pool. You have a lot of dirty blocks that eventually have to get written out. If the engine can't write back the dirty pages fast enough, there's usually stalls. It is in Python, so eventually, as engines are getting faster, I need to rewrite it into something faster. So bench marketing, I'm just giving you a big bar. Insert benchmark on a small server. This is an Intel NUC that I have under my desk at home. 8 gigabytes of RAM, 2 cores, Samsung 850 EVO SSD, so TLC lower, or what I would call a slow SSD. MongoRocks here is pretty fast. Definitely a lot faster than WiredTiger and mmapv1. In this case, I'm doing the test with fsync on commit disabled. The op log is there. There's no sync on commit because I want inserts to go fast. It's kind of interesting that WiredTiger is faster or slower than mmapv1. And I've had quite a few results from this testing that I've done where mmapv1 did a lot better than I expected. But hey, if faster is better, we can insert faster. Not surprising because we have an LSM where they don't. If I try to explain the difference, I frequently use tables like this. And so here, if nothing else, I have enough data that lets me look back and try to make some description of what happened. The first column is the average insert rate. So MongoRocks is almost 10,000, much faster than the other two. The second column is a 99th percentile insert rate over 10-second samples. And so you can see the MongoRocks 99th percentile drops to half of what the average rate was. So there's still some instability there. The ratio for WiredTiger and mmap, well, WiredTiger is a bit better. If we look at how many disk IOs I did, IO reads per insert, significant difference between MongoRocks and WiredTiger. Not surprising, because secondary index maintenance is read-free. And this database does not fit in cache. So MongoRocks is not doing disk IO for index maintenance. WiredTiger and mmap are. Okay, that's a big reason why we are faster. Similar thing you can see in the IO kilobytes read per insert. And then finally, if you look at the kilobytes written back to storage per insert, we're just writing much less data. So we're more efficient. And then database size, MongoRocks is using less space than WiredTiger and mmapv1. And in this case, the database was not compressed. So I'm comparing 3 database engines that are not using compression, and we're still using much less space. Next phase was inserts concurrent with queries. Blue bar is inserts. The target is 1,000 per second. Green bar is queries per second. The first thing I notice is WiredTiger and mmap are unable to sustain 1,000 inserts per second. So they're kind of failing to run the benchmark as required. The other thing is the green bar for MongoRocks is just much better. So it's also MongoRocks, in addition to doing more inserts per second, it's doing more range queries per second. And range query is not the best query for an LSM. So I was happy with this result. If I try to explain this, let's look at the IO kilobyte written per insert. WiredTiger is writing back almost 4 times as much to storage per insert. And mmap is almost twice as much. The IO reads per query, again, are significantly more reads per query with WiredTiger and with mmapv1. And then finally, the last column, database size, and that's at the end of the test. The difference between MongoRocks and WiredTiger grows. And part of the problem is after the insert, it was 37 gigabytes for MongoRocks, 49 for WiredTiger. MongoRocks shrank a little bit, reclaimed some space from compaction, and WiredTiger grew, probably from fragmentation of the B tree. So, benchmarking, moving over to a large server. This is 48 hardware threads, 2 sockets, 24 cores, probably 50 gigabytes of RAM, fast, NVMe, MLC NAND flash. Again, MongoRocks wins. And here, WiredTiger is faster than mmapv1, but not that much. And so, as much as I like WiredTiger, and I think it has a bright future, for some of the workloads, it just wasn't doing as much as I expected it would. Again, if we look at some of the performance metrics to understand why, MongoRocks is doing fewer disk reads per insert. That makes sense because the non-unique secondary index maintenance is read-free. Kilobytes written back to storage per insert. WiredTiger is almost 3 to 4 times more than MongoRocks. Database size at test end. Here, MongoRocks, I think, was using compression. WiredTiger is using almost twice as much space, and mmap is using more than twice the space of WiredTiger, which is not a surprise. We take the next phase of the workload, 16 clients, each doing 1,000 inserts per second, so 16,000 inserts per second is the target. Blue bar is inserts, green bar is queries per second. Only MongoRocks is able to sustain 16,000 inserts per second. And mmap did substantially better on the insert load than WiredTiger. And mmap did better on the query workload than WiredTiger. But MongoRocks did the best. And these are range queries. Again, not the best for an LSM, but MongoRocks was the most effective. One other thing I recently did is added response time histograms. I'm trying to track down cases where there's too much variance in RocksDB. And so there's buckets for queries that complete in 256 microseconds, 1 millisecond, all the way up to 1 second. And then the numbers or the number of operations that completed in less than or equal to that time. So if you look at the histogram, it's shifted to the right for WiredTiger. So there's just many more slow responses with WiredTiger in this environment, including 8 queries that took between 256 milliseconds and 1 second. There's just more stalls right now. Same server, I replaced the fast SSD with TLC NAND flash. So I went from something that might do 100,000 IOPS down to 10,000 IOPS. So it was, let's say, 40,000 versus 18,000 inserts per second. MongoRocks actually did not lose any throughput on the insert rate. WiredTiger almost fell in half, moving to the slower storage. And this is a common thing when you move a B tree from faster storage to slower storage, it suffers more than an LSM because it's more dependent on random IO throughput. Step 2 was inserts concurrent with queries. And here I left out mmap. The target is 16,000 inserts per second. MongoRocks meets the target. WiredTiger was about 5,000, so it fell far short. Queries per second, concurrent, the green bar, MongoRocks again, far ahead of what WiredTiger was able to do. One interesting result, moving from fast SSD to slow SSD. Blue is insert rate for fast SSD. Green is insert rate for slow SSD. In this case, and I don't fully understand why, but I got slightly higher insert rate on the slow SSD with MongoRocks. Now, MongoRocks is only doing streaming I/O in this case. WiredTiger lost almost half of its insert rate when moving from faster to slower. Another interesting artifact I saw is I usually run this with 16 clients and 16 collections or tables. So each client gets a separate table. Then I sometimes run it where all clients compete against the same table, use the same table. So here's just the insert step on a server with a fast SSD comparing a 16 table result in blue with 1 table result in green. MongoRocks doesn't lose that much insert rate when moving down to 1 table. WiredTiger loses a lot, and so does mmapv1. I didn't try to explain this. I just thought it was an interesting result that in the MySQL space I see with TokuDB. So I was happy that MongoRocks is not suffering from this. That's all I have. So MongoRocks is available in Percona server, which is the version I've been using because I don't really want to build it myself anymore. I still run it on the hardware that I have, and I look forward to hearing from other people who have the opportunity to evaluate it. Any questions? Correct. So the question is, what's the comparison between MongoRocks and MyRocks? So I like people who work on a lot of these projects, so I try to be cautious about making direct comparisons. The insert benchmark I ran here, I ran on the same hardware for MySQL, and it's in my other slide deck. So if you take the 2 slide decks side by side, you will see substantial differences in the insert and the query rates, substantial differences between MongoRocks and MyRocks, and between WiredTiger and InnoDB. MySQL's far more performant today. WiredTiger, I'm sure will get there, but I mean, the performance results I can show with MySQL are very impressive on this workload. Unfortunately, I inadequately documented the case. So one of the results, let me scroll back to it. Yes, the testing I do, and I'll have a sequence of blog posts with a lot more detail. I test for the testing I did prior to producing the slides, I ran without compression with Snappy, LZ4, and zlib. Hopefully Percona server will soon have Z-standard, because Z-standard is just a better version of zlib. So yes, I just didn't identify the one case where I was using zlib for MyRocks or for MongoRocks. It'll be properly identified in my blog posts that follow this talk. The key with, frequently MongoRocks is generally not very sensitive to compression latency. The key is if you look at the LSM as a tree, you want to disable compression for the upper levels of the tree because there's no space savings. There's not much space used up there. And that data is frequently read, so you don't want to waste CPU. And then we use LZ4 for the middle levels of the tree, and then we use Z-standard for the max level of the tree. WiredTiger is more sensitive. WiredTiger with zlib suffers much more than WiredTiger with Snappy or without. And InnoDB is also much more performant without compression. So then one of the nice things, which I didn't really show here, is just MongoRocks and MyRocks are just much less, they're going to suffer much less when you're using compression in terms of response time. Any other, okay? Correct. Percona. Is anyone using MongoRocks in production that you can mention? You are? I was. Facebook was using it for parse. So it ran for more than a year, maybe 2 years, in production. Parse the business got turned off, and so that's why it's not being used anymore. Okay, thank you.